I'm Nathan Holland. I'm protocol architect at ON Labs, and I'm here today to talk about Mina's upcoming Berkeley hard fork. So today I'm going to talk about the Mina blockchain, just give a brief overview of the Mina blockchain for those who may not be familiar. I'm also going to do a deep dive into the Berkeley upgrade and ZkApps, which are coming with the Berkeley upgrade. And then I'll talk about the road to releasing the Berkeley hard fork as well. So what is Mina? Mina is the world's lightest blockchain. And what does that mean? It means that it has a consistent size. It's a constant size blockchain. It has constant time bootstrapping, so new nodes can bootstrap the network in constant time. There's no cap on the number of validators, and there's no need to store the entire chain in order to participate in consensus. It's scalable and trustless, meaning that we verify the entire chain quickly, and all the heavy lifting that's required to keep the blockchain light is done in parallel across the network instead of being restricted in a bottleneck per block producer that's producing each block. And it's accessible anywhere. The network can be joined and verified directly from the web browser or mobile phone, and there's no need to trust third-party nodes when you're interacting from the web browser, because you can actually join the network as a full node and operate on the network and send transactions directly and receive blocks directly from the network. And what makes this all work? The way it works is that participants in the network only have to verify the recursive proof rather than replaying the entire chain from the beginning. This block proof is made immediately available at each block. So every block you receive, you get the proof of consensus, and you're also getting a proof of some set of transactions that had happened in the past that lead up to the current ledger that you can take a look at. Full nodes store this proof only in the ledger. They store only the proof in the ledger data that they care about. In order to do this, they don't have to store the entire history of blocks like other blockchains do. And because of this, Mina can be accessed from any device instantly and forever. And so when you compare this to other blockchains are constantly growing in size. The more data that they collect, you're going to have to constantly keep that data around because you need that data to trustlessly verify the blockchain by replaying all the blocks. But Mina maintains a constant size because all you need is the latest few blocks in order to achieve consensus on the recent blocks and then the ledger. So for instance, like if you look at the full history of the Bitcoin blockchain, today it's about 435 gigabytes. And it takes about 8 hours to join the network and verify it from the beginning. Comparatively, Ethereum is 1.2 terabytes and takes even longer if you want to do full verification from the beginning and not trust any other nodes in the network. And Mina, by comparison, is in the range of megabytes. So where are we today? So we launched Mina back in March 2021. And since then, we've had about 290,000 blocks produced in the network. But you don't need all those blocks. Those are just the historical blocks. And about 355 staking pools operate on Mina today with a high degree of decentralization across all those staking pools. And there's about 170,000 accounts in the ledger today. So now I'm going to talk about Berkeley. Berkeley's the hard fork that we've been working on very hard since mainnet. And the biggest feature that Berkeley's bring is our smart contract system, which is called ZkApps. ZkApps are zero-knowledge powered smart contracts that can execute without the need for any kind of virtual machine. They support off-chain execution so that you can execute the contract locally in your computer without having the network to execute it, and then on-chain state to attest to your execution. And then proofs of you basically execute the contract fully off-chain and you just send the proof of your execution to the network. The network then verifies that proof, and then that proof gets composed back up into that blockchain proof that all the nodes are downloading. So what this means is that when you're actually syncing to the chain, you're verifying not just the transactions of like normal payments that happen in the ledger, you're also verifying the execution of every smart contract that happened, but these executions didn't happen on chain. So comparing this to traditional smart contract model, in traditional smart contracts like Ethereum, you don't actually execute the contract locally. You send a transaction to the network, and then every node in the network, when it receives that transaction, includes it in a block, is going to replay that transaction to make sure the block producer didn't lie about the state that was achieved after executing the transaction. And every node that needs to join the network has to do O of N checks for every transaction that ever happened if they want to do it trustlessly. Because of this O of N check and how expensive this is, most nodes in the network are just going to basically trust the state. A lot of people who are running nodes are not always verifying from the beginning because it's just too prohibitively expensive to do so. Comparatively, ZkApps on Mina, just like I explained before, we do the local execution and then we submit the proof to the network. And then each node just verifies that proof when it's received. But once it's included into the block, it gets recursively composed up into that blockchain proof that you download, so that you're getting the verification of every prior transaction. So when we join and bootstrap to the network, we're doing an O1 verification. And so the way you can think about interacting with a ZkApp is you can imagine that a ZkApp is living in your browser or on your local machine, and then the ZkApp is reading or writing state to some kind of off-chain state or attesting the private data that's available on your local machine, and then it sends a transaction to the Mina network, which then will write state on-chain to attest to whatever private data you used or any off-chain state that you read or wrote to. So one of the things that's really cool about this design is that this design makes Mina one of the best settlement layers for L2s. The reason for this is because since execution is happening entirely off-chain and is later posted to the chain, ZkApp transactions can represent state transitions of arbitrary size. Normally if you're working with a transaction on Ethereum, you're only representing these small step state transitions. But because these are all proofs and they can be recursively composed, you can have a whole bunch of small step state transitions that get composed up into a big step state transition and post that to the chain whenever you want at your leisure. And so L2s are free to operate completely off-chain as they see fit, and then settle to Mina at a later date. This allows L2s to sequence both off-chain and on-chain. So they can use on-chain sequencing of actions. They can then process those off-chain, or they can completely sequence off-chain. So it gives a lot of flexibility to how L2s operate on Mina. And because all those proofs are composed together onto Mina, the L2s, it allows L2s to cheaply consume state of any other smart contract that's on Mina. Because all the L2 has to do is if it wants to read state from Mina, it just checks the latest Mina block, and then it looks up an account there, and that account has already been proven on Mina, so that state of that account is already proven by whatever contract's running on the account. So I want to talk briefly about some of the features that ZkApps will have at launch. ZkApps supports custom token hierarchies, and that allows to have parent-child relationships between tokens that you can enforce permissions and rules and how the tokens are going to interact. It has a call forest model for allowing contracts to call into each other, and this allows you to create a series of dependent account updates from within one contract so that a contract will only succeed its execution, its proof is only valid if all the other interactions it expects have happened in the system. It has a rather robust permission system that allows you to specify which parts of an account state can be updated by which types of authorization. And since we support authorization by proofs, that means that you can have programmable authorization for different kinds of state updates. So for instance, you could let some fields of state be written by any user to sequence new things to happen on the chain. And then you could roll those up in another state, and that state can only be posted with a proof. And there's all sorts of other use cases there and things you can do with that. Contract executions can specify preconditions. Since you're doing off-chain execution, right? You're doing this against some state, and you might have some assumptions about the state of the blockchain. So you can specify preconditions that that proof is only valid under. And with the way Mina works, it will check those preconditions before including that transaction in a block. And the Mina's transaction proof circuit will actually make sure it enforces that those preconditions have to have matched in the block it was included in if the transaction's marked as successful. So this fixes the problem of like doing an off-chain execution, but perhaps the off-chain execution you did is now conflicting with some other off-chain execution somebody posted to the chain. And smart contract interactions can be sequenced on-chain, as I alluded to before. I gave the example kind of with permissions already, but you can basically submit actions to the chain and treat the chain itself as a sequencer, but do the roll-up off-chain. So somebody is then going to take the sequence of actions that you posted to the chain once consensus has been achieved on them, and then they'll roll up those actions and post the roll-up to the chain. And this can be done in a permissionless way too, so that you can even open up the action of this rollup and not have it be centralized. Anybody can go and do a rollup because all you're doing is you're just posting a proof. So a few examples of ZkApps that you could write is having attestations to data. So for instance, attesting to identity or attesting to asset ownership without revealing who you are. So just attesting to certain aspects of your identity, not revealing your identity. And what's cool about Mina is that because we compose together all the proofs and all the smart contract executions, that means that it's sort of like a roll-up of data attestation. Because what you get at the end is a blockchain proof that will contain the proof of every attestation that every smart contract's ever made. So you kind of get one big rollup of all the attestations. Another use case is to import the state of other blockchains via rollup proof. So if Ethereum has a rollup proof, you can import that into Mina, and that gets rolled up into the Mina proof. So that means it's, in that sense, Mina sort of can be thought of as a rollup of rollups. And that's part of the reason that the L2 story is so interesting and unique to Mina, because that's what L2s are nowadays. It's like they're rollups off chain, they post the chain, and then we roll up all the L2s together. And this makes Mina very usable as a cross-chain settlement layer for all sorts of chains to communicate. And another example of what you could do is you can implement private transactions within the L2. Because Mina is ZK native, the smart contracts already support ZK. It's very cheap to do zero-knowledge proofs inside of them. So it's much cheaper to do different zero-knowledge interactions. But you can implement those again on Mina, and you can even do other kinds of private transaction models, such as like Zcash embedded in Mina. And then because of the smart contract layer and the fact that everything's zero-knowledge proofs, you can have smart contracts that are in the L1 that are public call into the private transaction world and get guarantees about certain interactions that happen there without knowing who sent funds or where the funds were sent. They only reveal the limited part of information the user is willing to reveal funds. So I'm going to talk a little bit about some implementation details about how Mina is implemented, and specifically ZkApps. So we have a core proof system called Kimchi, which is written in Rust, and then a separate recursion layer called Pickles, which is written in OCaml. And the way that we implement all of the circuits is we have an embedded DSL for zero-knowledge programming called Snarky. That's an OCaml. And at the protocol level, we have an abstracted implementation of transaction logic, which basically defines both how you apply a transaction and how you prove that a transaction was applied. So we have one part of our source code that has a very long description of exactly what it means to apply transactions to ledgers. We can play that against a ledger and get a new ledger output. And then we can also take the two Merkle roots of the ledgers and run that same code to generate a proof. And this makes it really easy for us to have confidence that when we're doing the out of snark ledger application, and then when we want the network to go approve it, that those will be the exact same operations. And then in order to enable smart contracts, we cross-compile Snarky to JavaScript, and then we wrap it in a library that we call ONJS, which exposes TypeScript bindings that are a little higher level than Snarky. So you can still write circuits in them, but it's really custom tailored to writing smart contracts. It makes it very easy to write a smart contract in the Mina system. It's using the same proof system. It already supports pickles, and then it has the right shape of the proof that you actually need to send to Mina. And the way we make this all work, one of the important features in the proof system that makes this actually possible is the fact that our proof system supports siloed verification keys. Normally, when you're doing recursion in the Snark, you have to commit ahead of time to what circuit you're going to recurse over. But with sideloaded verification keys, what you can do is you can say that existentially, there is this verification key that exists, and now there is this proof that is valid against this verification key. And so users can go and build their circuits for their ZkApps. They can post the verification key to the chain, and that is essentially how they deploy a smart contract. The chain is storing their verification key, and the transaction proof is just saying this verification key from the account is valid against the proof they sent. So what's left to release Berkeley? Well, as Brandon just mentioned, we now have the ITN ready. So we're going to do, the incentivized testnet, that's our acronym. The incentivized testnet will happen on October 17th. Right now, the Berkeley hard fork is approved by the community. We wrote an MIP, a Mina improvement proposal. The community has voted on it, so we will be shipping it to mainnet. The implementation is feature complete, and we have thoroughly tested it at this point in time. So there's no other expected major changes to it. The incentivized testnet will run for a few weeks. And then if everything goes well in the incentivized testnet, there's no major issues, then we should be launching the hard fork shortly after that at some date. So if any of this was interesting to you, if this excited you to learn more about Mina, I recommend you get involved. We have developer documentation. This is a landing page that you can visit to learn more about Mina. It tells you about how to build a ZK app. It links to our ONJS documentation, and also tells you about programs you can get involved. And also check out our Twitters. We have a Twitter for Mina Protocol and ON Labs as well, where we talk about Mina quite a bit. So I hope you learned something about Mina, and thank you.